Okay, I think it's time to start. Welcome to the second lecture in the course. The title of the lecture is 3D printers, working principles, types, and pros and cons. Or alternative title is the lecture with the many acronyms. However, I will try to take it slowly and go over them carefully. I have the same conflicts of interest as last week's lecture. So this is the agenda for today. I will start with general principles, then go into the most common printer types, then go on with pros and cons, accuracy, and lastly, the setup at our hospital. I would like to point out that there are plenty of material at YouTube when it comes to printing techniques and practical printing tips. So this is just scratching the surface. The general principle is that the object is built layer by layer. We are adding material in each layer, and actually the correct term for 3D printing is additive manufacturing. In this course, I will be using the term 3D printing, but it's actually a bit sloppy uses of the terminology. The height of the layers we are building are typically, say, 0.1 to 0.2 millimeters. I will start with the most common and perhaps the most simple technique that is called fused deposition modeling, or FDM. The company Strategist registered the trademark for FDM in the late 80s, and we're also holding a lot of patents. So the big explosion of home printers occurred when some of the old patents expired. A synonym term that is not trademarked is fused filament fabrication, or FFF. So fused filament fabrication and fused deposition modeling can be used interchangeably. I will use the term FDM throughout the course, just for the sake of simplicity. The principle behind the technique is that the thin filament is melted in a hot end and extruded to create an object. The head can move in the X and Y plane, and the build plane can be moved up and down. I often try to describe the printer as a computer-controlled glue gun. Here is an example of how an FDM printer would print in vertebrae. The colors does not represent different material, but the different regions of the printed part. So let's start the video. So the dark yellow is a raft, so that helps the print attach. The blue is support structures, and the brown is the outer edge, and the yellow is the inside of the object. I can try to play it again. So the dark yellow is a raft, and the blue is support structures, and then the print. So we're actually not filling the object. You can see we were printing it with an infill, which is the interior of the print. The blue support structures are manually removed before the print is finished. Sorry. As I mentioned, an important limitation of technique is that it cannot build structures in mid-air. Therefore, the printer prints support structures that later needs to be removed. This image shows a preview of a print in another slicing software. And in this case, it's a mandible instead of a vertebrae. The gray structures are support structures in this image, and they are added to the print. So by rotating the print, we can minimize the support and where it's placed. So this is quite important. So there's a manual process of controlling the print in this way. And you always use different softwares to basically slice your objects into slices that are then forwarded to the print. So in this case, someone forgot to properly remove the support structures. FDM machines comes in all sizes and price. They're ranging from very inexpensive play-at-home machines to various degrees of sophistication, and the materials can often that can be used. The machine in the middle has two print heads that can be used either to print different colors of two materials, or one of them can be used to print the support structures in a water-soluble material. Then the support material can later be dissolved. One of the strengths of the MTM is that there is a very large range of different materials, colors, and special types of filament. The easiest and cheapest material to print is in PLA. And you can see on the left there's a lot of different material names that all have acronyms. And the acronyms are for the different plastic names. And personally, it's hard to remember all of these, and I don't see there's a big point of actually remember exactly what the names are. But the PLA material can be recycled and manufactured by corn fibers. Top right is another filament. It's a flexible filament where the result of the print is a bit foamy, and how squishy this is depends on the printing temperature. And the bottom right is a pretty cool material that is neutron absorbing. Left of that is a carbon reinforced filament. And if one wants a bit more happy prints, one can use the rainbow filament color a bit to the left. And in these times, one can use antibacterial filament that includes copper. For some of the different filaments, there are special considerations, mainly that many of them are hygroscopic and absorbs water and needs to be stored in dry packaging, preferably vacuum packaged. Before usage, one often needs to dry them if they've been opened before. For more low temperature filaments, we use a filament dryer that we made from a mushroom dryer. For other ones, when we need some kind of higher temperature, we used different ovens, in this case, my own oven. Next, we switch to the PolyJet technology. For this technology, small droplets are deposited and curated by UV light. Multiple colors and materials, both soft and hard, can be mixed. This is really cool, as you can print one part of the print as a soft material, another part and harder material. You can, for instance, print a tube where the elasticity changes along the tube. Finally, it's possible to have water or chemical soluble support structures. The PolyJet technique is a much more expensive technique compared to the FDM technique. Another similar technique is better binder jetting or inkjet printing. Here, the position of an agent on two layers, which is usually made by powder, and then it adds a binding layer and heat or light that fuses the two layers, and they are fused where the binding layer is applied. And this way of printing also allows for multicolor printing. The next method is selective laser sintering. Here a laser sinters and fuses powder together. For each layer, a roller is applying a fine layer of powder. A laser fuses the material at indicated points. Then the process is repeated. The advantage of this technique is that for plastic powders, there is no need for support structures. And the powders can also often be at least partly reused, not 100%, but partly. So the SLS technique works with both plastic powder or metal powder. The metals can be iron, titan, bronze, or sometimes other materials. Sometimes the laser is replaced by an electron beam instead. And often this entire process is kept in an atmosphere of noble gases or other non-reactive gases. Nowadays, it's possible to print in the metal humanium, which consists of old weapons grinded to refine powder. Printing in this material requires a certificate on which the purpose of the print is. Next out in our list of printing techniques is stereolithography, or SLA for short. The principle here is that the laser beam is hardening a liquid polymer with light. And the liquid polymer is often called resin. For each layer, the laser eliminates parts that should be hardened, and thereafter the plate is lowered slightly, and the process is repeated. Some printers are able to print in multiple different materials, depending on the resin use, although only one material per print. The range of the cost of the machines is again several orders of magnitude, depending on print size and speed, etc. Next out is direct light processing. This technique is really similar to SLS, but instead of a laser sweeping over the entire area, the entire area is illuminated by a projector in a shorter flash. This makes DLP machines much faster than SLA machines. Both SLA and DLP require support structures, and here is an example of a scaffolding support structure that is used for the Formlabs machines that we use. Which printer technique is the best? This is a really hard question. So the myth about the all-around 3D printer. There is not really all-around 3D printer that's good for all aspects. Therefore, the answer is that it really depends which is the best printer. One thing to remember is that service provider may be a great way to try new technologies or expand capabilities for certain projects. And it's actually possible to start a clinical 3D printing by only using service provider to do the printing, at least in the beginning. So what are the pros and cons for the different techniques? So please note that this is a highly subjective table, and in this case we are really comparing apples to oranges. Firstly, regarding cost, the FDM technique is a really inexpensive technique. The SLA and DLP are also quite inexpensive. SLS and PolyJet are more expensive techniques. Regarding speed, FDM is likely the slowest technique. SLA is a bit faster. DLP is the fastest of them, and SLS and PolyJet and jetting about the same speeds as a principle, at least. The levels of details you can print, so how small are the details that you can get in the print? Can you make a small screw, for instance, and get the threads for that, and really small details? So with FDM, you're not able to do super fine details. So SLR has quite fine details you can print in. DLP about the same, but it depends on the cost of the machine. So SLS, really high details as well, also for the PolyJet. Jetting, I'm not really sure, so I put 0 there. So how fail-safe is the technology as such? My feeling is that the FDM technique is the one that fails most often. Not because of the technique it's such, but often the prints are quite long, and then something can go wrong during the entire process. Otherwise, the other machines are probably quite about the same in how fail-safe they are. And it really depends on the application, of course. The number of colors, so with the FDM techniques, 1 to 2 colors, depending on the printer. There are some techniques right now where basically you put the machine before the printer, and that machine splices the plastic filament and figures out ahead which color to feed to the printer. For the test prints that comes out, it looks really great, but I haven't seen anyone using it medically, so I think it's might not work as good as expected for if you have really lots of different switches between the materials as you might have in some of the medical applications. For SLA, DLP, and SLS, you're limited to only one material. PolyJet can have a lot of different materials. Yes, and also colors. The same with jetting. They can have multiple colors as well. Regarding transparency, so FDM is you cannot print transparent in that. You can print transparent with SLA or DLP with the PolyJet technology. The next column is more on how hard it is to do the post-processing. Again, it really depends on what you're printing. But generally, FDM and SLA and DLP, there's quite a lot of work with the post-processing. SLS a bit less because you can sort of dust off. And the same with PolyJet can take some time to remove the support structure by requiring water soluble, etc. But please note that this is really generalized table, and it really depends on what you are printing and how many objects you are printing in the same object in the same print, etc. So it really depends, and this is the hard thing because, as I said, there are no all-around printers, and the advantage of each print really depends on what you print. And if you have setting up a clinical 3D printing center, it might be hard in the beginning to know what exactly are the types of things that I want probably going to print. So things to consider when buying a printer. So do you need multicolor? Do you need soluble support or no support to be able to print without any support? What's the complexity of your prints? What's the build volume that you need? So how is your biggest print going to be? How fail-safe do you need it? Of course, what's your budget for purchasing? But also what's the cost per print that you expect and are ready to pay? What's the service contract or the fallback strategy if the printer fails? So maybe if you buy an expensive and really stable machine, it may still fail, and then it takes a day or so before you're up and running. If you're 2 printers, then you can print on the other printer that hasn't broken yet. So there are all these considerations. Yes, so printing times. So our longest print was about 100 hours. So it's a pelvis. And our shortest prints are about 1 to 2 hours. In general, I recommend our clinical users to think that printing is at least an overnight process. And what takes time is really the manual time is the segmentation that we will go into the next lecture. So here I will show a small video clip on how it looks when the print comes out of the printer. So this is a video that Philip made. So this is a spine that we printed. So this is not the full-size spine, so it's a 70% spine, and it's sclerotic patient, no, scoliosis patient, sorry. Okay. So here I have a time lapse of the print. Actually, you can see it's small parts failing, This is how it looks when it was finished. And here, Philips lifts the plate out from the printer. And he will now start the cleaning process to remove the support structures. And we will soon speed up this process because it takes quite a while. So basically he goes at it with pliers, and this takes time. At least it's a job that where you don't need to think that much, so like a bit meditative of removing support structures. So this is about how it will look when it will be finished. Okay. So for instance, when printing in titanium, post-processing comes to a completely different level. And it's important to consider post-processing already in the design process. I will come back to this in the lecture where we'll go from images to ready print files. Often, I typically divide the print into multiple parts that helps the doctor to see the inside details better, and also significantly helps the process of removing support structures. Here are some examples of print failures, and actually these have only been the minor print failures. The worst ones we did not really remember to take a photo. So print failures do happen for all different techniques. 3D printing or additive manufacturing has some unique features that enables it to produce parts that simply cannot be manufactured in any other way. So the top left is a ball with another ball inside. So this was created by printing in two materials. One was the orange material, and the other one was the soluble water. The small teddy, the bottom left, has tiny hinges for the feet and arms, and that's printed in one piece in SLS technique. The top left, the ball, was printed in using FDM technique. And in the middle part here, that's the as a part of a suspension mechanism of a small remote control car. That's also printed in one piece. It really comes out that from the printer, but all you need to dust it off properly. Yeah, sorry. So here are some material comparison for some of the materials that we frequently use. And here are the names for them. And I also had put the prices. So it's directly clear that the PLA is very cheap. Remember that we do not print solid objects either. So in practice, it may be 1/10 of the cost of SLA or SLS materials per printed milliliter. Note that for the SLS, the price per part really depends on how much of the unsintered powder that can be reused and how well you manage to pack the printer. So it's important there to pack the printer properly. Yes. Unfortunately, many of the printing techniques, as I mentioned, are only limited to one material. One thing that we have developed is to make certain structures rugged, and this can easily be seen in the print here. So this can be used to highlight different parts of the prints. In this case, The rugged surface is used to indicate that there's calcium in this wall. Okay, so now we come to a really important part, that is accuracy. For medical purposes, accuracy is obviously really, really important. But firstly, what do we actually mean with accuracy? Do we mean that the dimensions are correct? Does it mean that they are anatomically correct and that the model is appropriate for the intervention? So let's start with dimensional accuracy. So firstly, this really comes down to the segmentation. And actually, it even starts before that because of the acquisition. So how accurate is your acquisition process? In MR, for instance, you may have quite large deformations of the images because based on inhomogeneous gradient fields or chemical shifts, and based on the materials. The best segmentation accuracy you can theoretically do is plus minus a half voxel, but often you're way less than that. Depends on noise and other things. So you have the segmentation errors, and they are much worse if you have image artifacts that can show lines and streaks that hides things in the objects, in the volumes or so. Then when it comes to dimensional accuracy, you have the print accuracy. So for one thing, you're limited in the layer height. You may be limited in plane resolution. You can be limited by Z compression. So that's, for instance, when the laser hits the surface or melts the powder, that it penetrates deeper than just the top surface. The most important dimensional accuracy considerations are where we could call as a name like the heat deformation. So that's typically something called warping and shrinkage. So everything that cools down becomes smaller, and this really warps and bends the materials. So let me show you an example of that. So here's a plate that we printed. So when it came out from the printer, this is printed on an SLA machine. So directly after it's printed, it's washed in isopropanol, and then you continue to curate it in UV light. So when it came out of the printer, it was completely straight. And dimensional accuracy is really high, and we're close to the building layer of 0.1 millimeter or so. So it's excellent accuracy. And then after curation, the plate bend, as you can see in this. So this is a really concern that you need to think of on how do you. It partly is how you construct this. And also another accuracy consideration that is really important is how do you place the part in the printer? So do you place it straight like this, or do you angle it in the printer? So there are lots of tricks of this, and here I recommend there are lots of materials on YouTube on this. Okay. So what I think is actually more, or just as important, or even more important, is what I would call anatomical accuracy. And this really depends on the application that we're using. And remember that what we're doing is we're creating anatomical representations or printed representations of the human body. And here, basically what we do is we take away a lot of things. So we're only selecting the things of interest. I'll come back to this principle in the next lecture. But it's really important that we don't remove things that is needed for the clinician to correctly interpret the model. So this is one important aspect of anatomical accuracy. And as I said, it depends on the application. So for instance, in cardiology, the volumes of the heart depends on the heart phase or the loading conditions. So here, basically, dimensional accuracy is not a big concern really, and because it really depends, and that will depend on from day to day conditions. What is more important here is to pay attention to things that really matters. So, are there holes between two different vessels? Are there holes between the chambers or the atrias? Or and do you get those accurately represented in the printed models? And to make sure that you don't get a hole where there is no hole, etc. That's really important. Maybe to make the model easier, you cut away some vessels from the model. So are these vessels you cut away important or not? In congenital heart disease or other congenital diseases, the child is growing. So often maybe the CT is done at 6 months of age, and then the surgery is done at 9 months or a year. You don't want to repeat the CT. So it happens a lot with the baby between that time. So that's a concern. In orthopedics or other bone applications, bone growth could be an application or a consideration. So for instance, for the neurosurgery cases, we avoid using CTs that are older than 5 months before they're used. The model is used because there might be some bone growth that could be considered, and for other applications, bone growth may be much faster. So it really depends. If you want to have include planning procedures, what's the cutting precision that's going to be used? How thick is the blade that the surgeon is going to use, etc. Or maybe what's the angle accuracy that you can achieve. For other applications like soft tissue or tumor cases, tumor growth is an obvious concern. And then, of course, segmentation can be really challenging in tumor cases. So if you look at each voxel in the image or pixel of voxel in the image, is this really a tumor? Is it not? So that's really hard sometimes. It depends on the type of tumor and the imaging, if it's an MR sequence or a CT or so. Sometimes you want to have include in the model a resection margin. So how big should that be? And that needs to be discussed with the clinician. If you create your model based on both either of maybe CT and MR images, and then you fuse the images, what's the registration error after doing that? And that will, of course, have implications on the errors that you can expect in your images. When you do prints that would be used for device testing, elasticity is a big concern. That often your prints are completely rigid or softish, but is the correct elasticity that you have in your model, and that could be really crucial. So that's a really hard problem. So one thing that I think is really important based on the accuracy is to always discuss with the user of the model so that the user understands each model's limitations. So you need to take this discussion each time, basically, or at least for each application. So what are the anatomical limitations? So basically, what were the parts that were cut away? And what's the technical accuracy? So these are really important limitations, and they need to be communicated to the user. When I started with the clinical 3D printing, I I expected that the accuracy or the technical accuracy, that it should be completely dimensionally correct, was more important than it has been in many applications. But it really depends, and for some applications the accuracy is really crucial. So a bit on the current setup at the hospital. So we have 4 FDM printers. So from the left is an Ultimaker, a bit old model, so purchased many years ago. So that was in a way the starting point of the center. We continued with a Raise 3D Pro printer from Raise Technologies. That's the one I showed before. They have 2 different heads for that. This has been one of our workhorses for the center in at least the early days. Then we bought a BNC Sigmax. This printer has 2 heads, but they sit on the same axis, so you can print 2 things at the same time, either a copy or a mirror. And then we have the APM Tech M220 that we will use for creating PEEK implants, so the medical grade PEEK printer. So these are our FDM machines. So this is the current setup at the machine that we have at the hospital for the FDM machines. So from the left, so these are all Formlab machines. So from the left there's a 3B printer, there's a free printer, and then there are free Form 2 printers. The black boxes are washing and curation stations. So we have a separate wash station for when we wash the models that we use for that will come in contact with that needs to be sterilized. So like that we print in the material called surgical guide. So like the things that we will do in neurosurgeons. So we keep these wash stations separately, and we also have dual wash stations for that, and then we have 2 curation stations that are used to harden the prints in UV light before they're finished. We can really see that the room is really cramped, and that's one of our main limitations right now, that we're looking for bigger rooms in the hospitals. And the room is really cramped with all the filaments and resins that you need. Okay, so this is basically it. Slightly shorter than expected, but it leaves us for 20 minutes for questions. I've seen some of the questions popping by as a lecture, but it's hard to read them at the same time. Let's see if Erik, are you online, or did you have to run away with short notice?
No, I'm here.
Okay. Let me try to see if we can get. Do you have a video as well? No.
No.
Oh,
not,
okay.
Not now.
All right. We'll fix that. But is it possible for you to moderate the questions today?
Yes.
Yes.
I guess so. So we have a question from Camilla, and it's already answered by Eric in chat, but it is, what does it mean with neutron absorbing?
Okay, yeah. So probably they're better explained in the chat than I presume, but the filament is used for when you're making experiments, like for instance the synchrotron radiation, create neutrons or other applications. So it's really a special filament, and for me this was an eye-opener that in filament that there are a lot of specific applications that I would never thought about, that before making specific shapes in neutron absorbing material was really hard, but now you can actually print it on a quite standard printer. So that was no eye opener. So that's why I included it.
Okay. Should we take the next one?
Hmm?
It's from Gabriel. And the question is, how is the radio opacity of different materials? And can it be varied? Say if one would like to construct a phantom for radiology.
Oh, that's a really good question. That one need to look into for the different materials. I remember I've Googled it for difference. Basically, most of the plastic filaments are quite transparent for the X-rays. And that's actually, for instance, for the peak filament that we had, I had expected that to be more opaque, which it wasn't. So, and this has really, it's both a weakness and a strength, because this allows you to see through peak plates, for instance, so you can see the bone healing, etc. So you can use it, and I think especially with all these new filaments like the carbon reinforced and some of them, I expect you could do as Gabriel then suggest that you could print in different materials and get the different opacities and create phantoms this way. So that's a great question otherwise. But most of the plastic are quite transparent in the way. So basically you need to experiment with them. And expect, for instance, the copper one, the ones that infuse with some copper or so, to be less opaque.
Okay, good. Then we have a question from Magnus. What is the best filler for post-processing PLA? Any convenient filler to seal the surface? And then you have some scenarios.
Okay.
Have you seen them yourself?
No, let me go here. Okay. So if you want to make a really nice smooth print, for instance, he used car spray and a filler and a paint, and I want to make the surface more durable and completely seed the model. Yes, this really depends on the material. One thing to get smooth prints, you can, for instance, print them in ABS, and then print put the printed part in a chamber when you have acetone in the same chamber, and that ABS is quite soluble to acetone fumes. So this creates a sort of, it basically melts the surface and can create nice smooth prints, or it can do different prints, etc. So it's yeah, there are different techniques, and I think Eric also gave some more details, and I would say YouTube also have some great tips here.
Okay, on to the next one. How do you sterilize surgical guide?
Yes, so here in Lund we use the autoclave. So and we use the standard autoclave program in Lund that is 134 degrees Celsius, and I think it's 7 minutes, but it depends on the size, etc. So we leave it to the sterile center. In the beginning, we started to before we had the SLA machines, we printed in nylon and tried to sterilize that. It seemed to work quite nicely if it was quite solid nylon and you had 120 degrees in the autoclave. But if we raised it to 134 degrees that they wanted at the hospital, this did no longer work. The prints deformed too much. You can use ethanol. There's some different ethanol mixtures that you can use for sterilizations, etc. The thing with these ones is that you really need to take care of that. You get away all of that. So that's typically not allowed to have for surgical guides, etc. At least in the hospital that we have. So they really prefer to have everything autoclaved. That's the standard, easiest method. And of course, not all materials are autoclavable. I would say the majority of materials are not. And if you have a gamma sterilization machine, this will be able to sterilize almost all of you have, but it's quite expensive technique. And it's not used as much. But we use autoclave.
Thank you. And then we have another question, which is the better sterilization method for PEEK implants?
Here I would definitely go with the autoclave, because PEEK handles the temperature perfectly. And so that would be the one I use. Definitely. And with the PEEK, it's important, since you're printing a filament, I presume, then you have an infill, so it's important that the infill is also sterilized. So the temperature in the building chamber needs to be higher than 100 degrees or higher than 70 degrees at least, which it will be.
We have a question. Do you also perform annealing to the PEEK implants?
We haven't finalized that procedure yet. I tested the annealing, and more experiments will be needed. So annealing is a technique where you basically, after you printed the thing, you put it in the oven, and then you raise the temperature to a certain degree, you hold it there, and then after a while you put it slightly higher and then let it cool again. So, and then the chemical bonds fuses better. I'm not sure if we will need to use it. Hopefully not. But it's something that we need to experiment more with before we have sort of clinical production in that.
And do we use any polishing tools to the post-process of PEEK implants?
For the PEEK implants?
Yes.
So there are some papers out indicating that the unpolished PEEK is actually advantageous in terms of how it adheres to the tissue, etc. Likely, however, we will use polishing where it's going to be needed, either where it's going to be close to a joint, when you're like going to do like this, or we are going to use it where we have the support structures attached. So, and the polishing machine we have is actually a standard dental polishing machine that can be used to grind it.
Yes. And then we have a question from Wolf. Did you try gamma radiation to sterilize surgical guide prints?
No, we have not tried it. I'm sure it will work if you have a gamma sterilization machine. It's just that it's not part of the hospital standard machinery. And the nice part of that we can use the hospital standard sterilization machinery is that then they actually deliver the printed parts directly to the surgery, and also with the same tools that are also sterilized by the same system, so to speak. But for sure, it will work.
Yes, and then we have a question from Vasilis. Do you have a special ventilation for your setup?
Ah, that one.
Yeah.
currently, I would say we have definitely inadequate ventilation in that room. So that's part of the things we are looking into when we're going to switch room. So if you're going to have a printing facility, I would recommend to have good ventilation, and also for a lot of for things, experiments or so, to have a what's the English name? Dragskåp in Swedish, like a cabinet where there's air sucked out. That would be advantageous to have at least close to the printing facility to experiment with different things. So right now we have inadequate ventilation, I would say, but it smells good sometimes when you print, for instance, the elastic, but it's not how it's supposed to be.
Let's see. So we have a question from Sasidar.
I can see here in the chat the fume hood, as it says, but
yeah.
It's dragskåp.
Yes, we have a question from Sasidar. Does the density of the printed parts plays a major role in implanting, or every implant which has to be implanted should be printed completely solid?
No, the cranioplasty prints we will not print solid. Not for the sake of sort of saving weight, more for that. If you have it printed solid, if you get a hit to the head, then it snaps. It will make an ugly snap. But if it's not solid, so with an infill, the crack is much nicer. So that's one aspect. Actually, for the peak, which is not super, so that's really transparent to to X-ray. We will actually have the possibility to see the print by the internal part of the implant will have lower density. So that's going to help us to locate the implant, as we have hard difficulties to see it also. So that's another aspect. So it will depend, but I don't think printing completely solid peak is hard, I expect. So.
Okay, and we have a second question from Wolf. Are there any materials besides PEEK that you use on patients directly?
So we use the surgical guide materials directly on the patients to ensure, so they are used in the wound, so to speak, but then after that we remove them. We have not come to the stage of printing in metal and implanting that, etc. And most likely, I don't think we will for many years have a metal printer at the hospital. I think that's going to be service providers that would potentially print that for us if we need it.
Okay, and then we have a question from Tommaso. Can all material be sterilized?
Basically, I would say almost all of them will handle gamma radiation sterilization. Quite most would not handle autoclave. So that's, yeah.
Okay. Gabriel has a question. How compatible are the different types of material with MRI, safety, artifacts, and so on?
That's a good question. I think no. So all of the materials that I can think of are compatible with MRI, with the except of sort of iron prints, but all the plastic ones that I can see are. We haven't tried some of the special filaments, like the adbor would be interesting to see. Probably will be completely black or so, but I wouldn't. It wouldn't pose any considerations I would see. It's the key issue here, if it's electrically, what's the impedance of the printed part, I would say. But for all practical reasons, most materials are definitely MRI compatible.
Yes, and then we have a follow-up question of Sasidar. How do you post-process porous 3D printed PEEK implants? And have you tried to sandblasting and microblasting?
We have not tried that. I've been thinking of it. I'm not sure it will be required. Depends on, because I think if you're after the porous structures, or if you want the PEEK parts to be porous, then I think you might as well basically leave it as it came out of the print, because that's have small irregularities that could be advantageous to use. And I'm thinking potentially in the future we might, when we print PEEK, that to have to really modify the G code or so that one part of the print is really solid and one part is less solid, and then if we wanted like that, so it could, so you can really steer it depending on how you want it. But sort of that's the scenario that will be in the future to look into that.
Yes, and then we have a question from Sverrir, and he wonders, what's the least toxic material?
I mean, I would guess that all of the materials that are classified as so in materials there are different classifications. So some of the filaments are food grade. So basically you can print your own lunchbox and then use it. And then of course the surgical guides, resins, they are much more tested and they are less toxic in that sense. And they tested really by implanting the printed plastic. They actually even test them to inject the uncurated plastic into the poor rabbits or so to really test the toxicity. But completely finished and curated surgical guide is really an inert and doesn't really involve, sort of nothing really happens with the tissue to that material. What your concern needs to be is more of the secondary infections and these kind of things with the materials rather than the toxicity.
Yes, and then we have the last question, and it is, what regulation, if any, do you follow for in hospital surgical guide anatomical model printing?
Yeah, so basically, I will come back to that in the lecture 5, but basically we will be producing medical devices, so it's classified as a medical device. And in that medical device regulation, there is an exemption that we can use in-house manufacture. So basically, we do all the documentation that is needed to fulfill the requirements of a CE mark, but we don't need to do a formal CE mark with external notified bodies to inspect us. So we use the hospital quality system. So that's the regulatory framework for the surgical guides, etc., that we are using already now with the neurosurgical guides, for instance. Mm-hmm.
So there popped up some more questions. Do we have time, or?
We can take one or two, and then we need to, for everybody's sakes, complete the talk.
Okay. So what are the mechanical properties requirements, for example, PEEK cranial implants, X, Y, and Z direction?
I'm trying to interpret the question, but I think the question is partly on how to orient the print, the implant in the printer, I guess.
I would guess so.
And for all filament printing, you have the weakest part in the Z direction. So the layers, then it's easy to snap the different layers. So I will probably put a bit on angled, but then you need to weight how much support structures you get. And for cranioplasty, you don't need that much strength because it's basically a lid to the skull. So I would be more concerned of getting a nice print than the optimal angle, I would say. So pretty much the ones that we've done now, we print pretty much standing to make it simple.
I guess we can answer the last questions in the textual Q&A, maybe.
Yeah, they're going to do. So yeah. This would then end this lecture, and the next lecture will be the process from imaging to finished print. And thanks all for today.